So, Wasim Tanashi, it's up to you.
Thank you. So can you hear me all right? Okay, so I'm going to talk about symbolic regression, so again, and how we can use it to discover new astrophysical laws. So the rationale for doing that is that, yes, that's how astronomy has worked so far, right? We have been conducting observations, and then we have discovered empirical laws that fit those observations. And then, so this is Kepler, and it actually took him 4 years, which is quite interesting. So we shouldn't complain about the running time of symbolic regression algorithm, maybe. I don't know. So, and then we devised general theories that encompass multiple empirical laws, and that's how we discovered geophysics so far. The problem is that as we are transitioning towards larger and larger surveys, it's becoming much harder to discover new physics, and the hints towards new physics are much more subtle, and that's why we use machine learning. But the problem is that these are largely black boxes, and that if we want to connect these newly found empirical laws in the form of neural networks to theory, we need to restore this link, and this is what I'm trying to do, to create this link and to connect with analytical laws and with theory, and in the hope of finding new physics. So this is the problem that is posed by symbolic regression. So the idea behind symbolic regression is that you're trying to find an analytical law that represents some data, and I mean everything, whereas the cosinus is there a cosinus, whereas the division, not just the constants, like we usually do. So that's why we devised our own symbolic regression algorithm. Will that work? No, not a good idea to do that? Not a good idea, okay. Oh, sorry. I'll go back. It's, oh. Okay. So the idea is that by trial and error, we're trying to get the analytical laws behind some data. So for example, here, these are the data points behind the Dent harmonic oscillator, and little by little, the algorithm will converge towards the correct analytical law. Oops. Okay, so why is that useful? So as I was saying, connecting with theory is written with analytical in analytical form, so this is important. Also, something that we don't think a lot about is that those models are much cheaper to compute than neural networks, so this can be also useful in that regard. Also, they tend to generalize much better than neural network due to their compactness. So how did we create our symbolic regression machinery? So we did it by basically using the tools that have been made to process natural language. So there are a few subtleties. It's not exactly straightforward to apply language processing tools to mathematical symbols, but that's basically how we do it. So I'll try to explain briefly how symbolic regression works, and since I think it's not the last time we'll hear about it during this week, I'll try to do a proper job. So the idea is that, so here it's symbolic regression with a neural network. So I think I'm pretty sure that everybody else is using genetic algorithm here. So with a neural network, but genetic algorithms are quite close to, you generate a categorical distribution of symbols, distribution. You decide to interpret it as a categorical distribution around the space of symbols, and then you can sample a symbol from that. Once you do that, you can basically do almost anything you want. So this is the infix notation we are more used to. And this is equivalent to a true representation, so you can represent an equation in that format too. And if you list each node first in depth and then left to right, you can have a prefix notation, also called Polish notation. And so this is also what is at the very heart of CPUs and stuff like that. So once you're in this notation, you don't need parentheses, and that's how all symbolic regression algorithms operate, basically. And once you do that, given a list of possible symbols, so for example, I have a toy library here, you can represent any equation as a matrix. So once you do that, you know how to go from numbers to an equation, and basically you can do all sorts of interesting stuff. So I will skip that, not super interesting. So what we have done so far is that we have basically just applied the principles of dimension analysis. So dimension analysis is extremely constraining. So for example, we all know that here, if we have a velocity and we add up a length divided by something, we all know that that something must be a time, right? So just applying this sort of principle while the equation is being generated allows us to basically restrict the search and diminish the search space size. So for example, here in this toy example I was giving before, this is the space of expressions that we have without dimension analysis, and this is the space with dimensional analysis. So this enables you to basically reduce the search space. So how do we do that? So basically we have our model. So here we are using a neural network. It creates a categorical distribution of across the space of symbols, sorry. And then we also generate a prior distribution which encodes the rules of dimensional analysis live, so in an incomplete tree. So this is a bit challenging, but this is doable. You can compute that. So for example here, since we need a time, it can be either a time or something more complicated that eventually leads up to being a time, but this is definitely not a length, a velocity, or a dimensionless operator. So once you do that, you can sample your symbol. And also, quite interestingly, this is only possible in sequential expression generation SR approaches, symbolic regression approaches. I will skip that too. So once you do that, you can basically create an equation. So for example, here, what we do in our work is that we give contextual information around the next symbol to be generated. So units information, all sorts of informations. And then from the neural network, we compute a categorical distribution. So the neural network is informed of that local information. We apply a prior, and then we sample a symbol. Then we repeat that a bunch of times, and we end up having a complete equation. So I hope it will work too. So now with the fun part. So what we do to train our neural network, oops. Advertisement, I think. No. Well, let me skip that then. Okay, so what I was going to show is that we just use reinforcement learning, and actually it's quite straightforward. And I was going to show a video of reinforcement learning being applied to a chicken. So this is really simple. So the math behind it is a bit more complicated, and I can go into detail if you want, but the basic principle is quite simple. The idea is that you have your neural network. It generates a bunch of equations. You reward those equations based on their fit quality or any other criteria you want, and then you reinforce on the best candidates. So if you do that a bunch of times, it will eventually converge towards a good expression. So something that is interesting here, and that is quite interesting here, is that actually the reward, since we are using reinforcement learning, it does not have to be auto-differentiable. So this is really different from other approaches, and I think it's something that we don't value enough in astrophysics, is that reinforcement learning enables you to have a reward that is not necessarily differentiable, and so you can do that in all sorts of contexts, not necessarily only symbolic regression. So since we can apply any physical constraints we want, even if it is not differentiable, we can use all sorts of criteria, so symmetries, constraints on derivatives, primitives, any sort of constraint you want. So this is, I was going to show how we reinforce, but I will skip that. So learning curves. So this is our neural network learning to generate accurate expressions, but also physically sound ones, so expressions that obey dimensional analysis rules. So we tested our system on 120 equations from the Feynman lectures on physics, plus other physics textbooks, against 17 other symbolic regression algorithms. So this is quite a standard benchmark. And these are our performances. So we are second to best in noiseless scenarios. And then as you increase the noise level, you can see that our algorithm is quite robust. So something interesting that was also mentioned just before, I think, is that you can use symbolic regression to discover new physics by just basically plotting the complexity versus accuracy of your search space, of your equations per search space. So for example, here we gave toy data of the energy of a particle against its velocity, and it was able to find the classical approximation, which is what you can see at the upper left, but also the relativistic expression at the bottom right, which is more complex but also more accurate. So this is quite an interesting plot to do. In conclusion, what I have presented is our framework, which we call FISO for Physical Symbolic Optimization. It can be used to resolve any symbolic optimization task while taking advantage of dimension analysis constraints. I will not repeat that because it's a bit boring. I will talk about perspective. It's more interesting. So the problem with symbolic regression right now is that almost all frameworks are guided by accuracy. So you have an accuracy and you improve fit quality. You try to improve fit quality over time. But the problem is that the path towards the best fit quality and the path in symbolic, in symbolic arrangement is not necessarily correlated. You could improve fit quality over time while not getting further away from the absolute minima in symbolic arrangement. So what we'll do in our next work is try to leverage data in a more meaningful way, and it's not, basically not using just a scalar reward. Something else that would be also quite interesting, and that is not of great interest to the machine learning community, to the purely machine learning community, I mean, is using differential operator and also introducing some sub-functions. I think we all know that if we open a physics textbook, it will contain a bunch of equations and not a very long equation. So having equations that reference each other and also differential equation, I think is the way to produce, interesting explanations behind data. So, one last slide. So it's our algorithm is open source. We have a lot of users and a lot of contributors, and you can use it if you want. It's as simple as what I've shown here. It's super simple to use. Yeah. Thank you for your attention. And sorry.
Thanks a lot. Thanks for this very nice talk. I'm sure we're going to have lots of questions. Aren't we? Okay, so I'll start first. So here you presented the overall machinery. What are the specific things you're interested in terms of astrophysics and cosmology? Because that's part of the game here.
So, I have, it's taken me a lot of time to produce this framework. But what I'm interested in is dark matter, so I will apply that to the galaxy profiles, hopefully trying to find a new galaxy profile and stuff like that. I think it would be quite interesting. Also, the velocity maps that we will have with the James Webb could be, I think we could use them in that sort of context, especially with differential operators. Does that answer the question?
In large part, yeah. Do we have questions on Slack?
Yeah, there's a question on Slack. The point about using dimensionality as a way to reduce your parameter space seems really cool. Could you explain how this would work for dimensionless parameters?
Sorry, can you repeat?
Could you explain how using dimensionality as a way to reduce your parameter space would work for dimensionless parameters?
Okay, so if you don't have, if there is no unit associated with the data, it won't reduce the search space. Does that answer the question? Yeah, pretty much. Okay. I hope that answers the question, but yeah, basically it takes advantage of units and the constraints in symbolic arrangement that arise from units. So if everything is unitless, then there is no advantage to take off, right? So it will just be the reinforcement learning framework that we have.
Okay. Any question in New York?
Yep. Right. Hello, Peter Milk here from Princeton. I have a question about how you represent the results of the dimensional analysis in form of a categorical distribution as a prior. These are relations between operators and quantities that go into there. So how can you express them as a kind of a prior distribution, a categorical distribution?
Okay, so if I understood correctly the question, it's you ask. So is how can we create this this units prior? So the idea is that yes, it's quite hard because you don't have all of the information because the equation is not complete yet. So it's a live constraint while the equation is being generated. So at some iterations, you won't be able to give any constraints. So for example, if you have nested multiplicative operators, the units can be compensated from either side of the multiplication symbol. I don't know if that's clear. I hope it is. So what we do is that we have an algorithm, it's detailed in our paper, that takes advantage of this as much as possible, as much as we can, with all of the information available while you're producing the equation. Does that answer the question? I hope yes. Yeah.
So we have a question here by Torsten, and while the mic goes down to Torsten, can I ask Jel Mess and Lucas McKinnon to please join me on the stage for the next talks, so that things will go smoothly. Torsten?
Yeah, so that's interesting. The prior you have on your functional space, I understand that it is derived from actually what humans use, right?
Yes.
So functions like Bessel functions or hypergeometric functions or all the possible mathematical functions one can write down are underrepresented. So have you thought a little bit about what is the meaning of the prior you are effectively using?
So this is a super interesting question that I get quite a lot, actually. It's that it's a problem in Symbolic Regression, I think, in general. We are using the functions that we as humans decided that were interesting, but this is maybe not the most fundamental functions that we have in nature, right? So I think the next step, like creating sub-functions that can be called into a more general equation, would be the way to do it. So if in a lot of data sets, you find that there are optimal sub-functions that should be used all the time, maybe these are the true fundamental functions that we need to use, and this should be detected by such a system, which would have a sub-function. Does that answer the question? Yeah, I hope so. Yeah.
Is there a very last question in New York? Otherwise, we'll go to the next talk.
No, I think we're all good in New York.
Okay, well, thanks again.
Thank you.